Today, it is my honor to present our team's work, received at ICCV 2023, Dynamic Snake Convolution based on topological geometric constraints for tubular structure segmentation. Tubular structures, prevalent in both medical and natural scenes, play a pivotal role in various domains. Accurate segmentation and localization of these structures are essential for numerous downstream tasks. In the medical field, for instance, coronary artery disease stands as one of the world's leading causes of mortality. It is primarily attributed to regions of abnormal narrowing that compress blood vessels, leading to disrupted blood flow. CTFFR, as a reliable technology, utilizes computational fluid dynamics to non-invasively quantify functional stenosis in precisely modeled coronary arteries. However, a critical prerequisite for its success is the accurate segmentation of blood vessels. Accurate segmentation of such narrow structures presents a formidable challenge. The main difficulty arises from their thin and fragile local features, coupled with their complex and variable morphology. Recent segmentation models, particularly the Segment Anything framework, have gained prominence. We attempted to apply this framework to tubular structure segmentation, but encountered difficulties due to the slender and low-contrast nature of these structures, resulting in suboptimal segmentation, as depicted in the images. Additionally, existing methods struggled with complex morphology, as evident in the road segmentation results, where severe discontinuities disrupt downstream tasks. Inspired by deformation convolutions, we embarked on a journey to design a network that could adapt dynamically to such intricate structures. These deformations guide the convolutional layers to focus on key features. However, during our initial experiments, we observed that due to the small proportion of tubular structures, the model inevitably lost perception of these structures, causing the convolutional kernels to drift away from their intended targets. To address this, we envisioned a network architecture tailored to the characteristics of tubular structures. We aimed to create convolutional kernels that could both flexibly adapt to structural features and stay reasonably close to the target structures. Inspired by the continuous, sinuous motion of snakes, we introduced dynamic, snake-like deformations into our convolutional kernels. The image illustrates the model's improved focus on features, demonstrated using 2D retinal data. Regardless of the direction or thickness of the vessels, our snake-like convolutional kernels adapt more effectively to the elongated structures and capture core features. Given that the orientation and perspective of tubular structures are inherently diverse, we found it imperative to incorporate multi-perspective features in our design. However, fusing multiple features inevitably increases network load and introduces redundancy. To address this, we implemented grouping and random dropout strategies during feature fusion, mitigating memory pressures and preventing overfitting. Our ultimate goal is to construct topological structures from data and extract high-dimensional relationships within complex tubular structures, such as continuity. The topological loss function we designed, grounded in continuity, has been effectively employed in previous works. The topological constraint proves particularly effective for slender and low-contrast structures. We employed Hausdorff distance to measure point set similarity, enhancing the model's focus on discrete points. This concludes our comprehensive framework design. In this research, we utilize 3 datasets, comprising 2 public datasets and 1 proprietary dataset, to validate our approach. In 2D, we evaluated the Drive retinal dataset and the Massachusetts Rhodes dataset. In 3D, we employed a private CCTA cardiac dataset and later validated on the 3D KEPA public dataset. Visual results demonstrate the effectiveness of our approach in segmenting tubular structures, particularly in remote sensing road data and coronary artery vessel data. Our proposed framework has been specially designed for slender tubular structures, successfully merging morphological features with topological knowledge to guide adaptive segmentation. It remains an intriguing topic to investigate whether similar paradigms apply to other morphological structures and can improve their performance in feature discriminate structures. Furthermore, we are actively working on optimizing this framework as a universal architecture within large models, providing a viable paradigm for distinguishing features in these challenging structures. Thank you for your attention.